So what is a linear transformation? A transformation is a technique in which a vector gets converted into another by keeping a unique element from each of the original vector and assigning it into the resulting vector. Now, as you can see in the slide, give the definition of linear transformation from a vector space V to a vector space W in bracket T V to W. So as you can see, there is two function that fulfills two primary conditions, which are additivity and also homogeneity. For additivity, when T operates on the sum of two vectors, which is U and V, within V it satisfies T in bracket U plus V equals TU plus TV. So next one is homogeneity. For any scalar k and vector v in V, this condition means multiplying the vector v in V by a scalar k and then applying the transformation results in the scale transformation of the original vector v by the same scalar k in W. So, in summary, a linear transformation maintains the principle of vector addition and scalar multiplication consistently from the domain V to the codomain W.
So for the question 2, we list out the properties of linear transformation. So we have three properties of linear transformation. So the first one is T preserve the zero vector. T0 is equal to 0. So the example, we have a linear transformation R2 to R2. So the R2 is a vector space of column vectors which contain two real numbers. So Txy equal to 2x negative 3y. This transformation takes a vector xy in two-dimensional space and doubles the x component while flipping the y components and scaling it by negative 3. Let's evaluate t at the 0 vector, 0 equals 0. Then we substitute the answer, we got 0, 0. When the 0 vector 0 is inputted the transformation t, the output is also the 0 vector 0, 0 in the codomain, confirming that the linear transformation t preserves the 0 vector. So the second one is t preserve the negative of a vector. So this is a formula. Then the example, we have a linear transformation R2 to R2 defined as follows. So let's verify the property that t preserves the negative of a vector. So we consider a vector v to negative 4. We will find negative v and compute t negative v and negative tv. So negative v, substitute the answer, we got negative 2, 4 and 2, negative 4. Negative b, so negative v equal to 2, negative 4 and equal to negative 2, 4. So we use t negative v and so we use t negative v and then the t negative v and we substitute the answer, we got negative c and negative 8. And then we try substitute negative tv and we got negative 6 and 8. So the third property is T preserve linear combination. So this is a formula. Example, we have a linear transformation R2 to R2 defined as follow. Take vector V1 equal to 1, 2 and V2 is vectors. Let's say C1 equal to 2 and C2 equal to negative 1. So we substitute the answer, we got negative 1 equal. So we substitute the answer, we got negative 1 and 0. And now we apply the transformation T to this linear combination and then we got negative 2, 0. This result satisfied the property of the transformation T preserving linear combination as the transform linear combination is equal to the linear combination of the transform vectors. So I will pass to third presenter.
Okay. So I would like to present for the third question, which is 3A for the vector. So the question says discuss the following linear transformation, WTV to W, by giving one example for each solution. So for the transformation for vector, I've given the example Rn, which is equals to xy, and then I've also given an example Rm, which is equals to x plus y, 2x, 3y. So based on the vector where I let x equals to x1 and x2 and y equals to y1 and y2. So based on this vector transformation, there's two rules, which is one of it is the vector addition, which is given by t a plus b equals to ta plus tb. So you can scroll down. Okay. So first from the equation just now, which is ta plus b equals to ta plus tb. The left hand side is t a plus b, which is equivalent to tx plus y based on the example. So when we conclude that, we solve the equation, the final answer is can refer from the equation 1. So we can substitute the x plus y, 2x and 3y based on this equation, this dx plus y. And we get for the left hand side. So for the right hand side, we do the same thing, which is x dy. And based from the equation 1, we conclude that x plus 1, x2, 2x1, 3x2, and the vector y1 plus y2, 2y1 and 3y2. So from the right hand side, from the previous equation, which is vector addition, from the right hand side, which is dx plus dy, we also follow the previous step, which was we based on the equation 1. So which is x1 plus y1 plus x2 plus y2, we will get plus 2x1 plus y1 plus 3x2 plus y2. So that's the final for the right hand side. Hence, for the right hand side and left hand side are equal. So this satisfies the rule of vector addition. So the vector of Rn and Rm, which is n and m, are equal to the vector n equals to 2 and n equals to 3. So for the next one is based on the scalar multiplication rule, which is TCA equals to CTA, where C is a constant. So for the next one, you can scroll down. So I let x equals to x1 and x2, the vector. So previously, like the rule, the scalar multiplication rule, the left hand side is TCX, where we let T and we substitute x1 and x2 inside the TCX. And same from the previous method. So we substitute from the equation 1. So we will get cx1 plus cx2 equals to, cx1 plus cx2, 2cx1, 3cx2. And for the right hand side, we can get ctx. And where we conclude, we can get cx1 plus cx2, 2cx1 and 3cx2. So can scroll down. Okay, so hence the left hand side equation is equal to the right hand side equation. So this satisfies the rules of scalar multiplication. So in conclusion for question 3a, the function tv to w is called a linear transformation if the vector space v and w satisfies the axiom of vector addition and scalar multiplication. So that's all for me. I would like to pass to the next presenter.
All right. My name is Armin Hafiz, and for the next linear transformation is for the polynomial. All right. The linear transformation that given to me is Pn changed to Pn plus 1. All right. First and all, let the transformation into P1 to P2. My P1 is A1x plus P1, and yeah, it changed to A1 x squared plus P1x. Right. I conclude my linear transformation from to in this my linear transformation about polynomial. Linear transformation increase the polynomial degree by 1.
For question C, the term linear transpose 3 by 1 likely refers to transposing a 3 by 1 matrix or a vector. Transposing a matrix involves switching its rows and columns. For a 3 by 1 matrix, it means converting a matrix with 3 rows and 1 column into a matrix with 1 row and 3 columns. So if you have a 3 by 1 matrix like in the that I present, transporting it will result in a 1 by 3 matrix. This operation changes the orientation of the matrix without altering its element. Hence, the transpose of matrix is given by interchanging rows and columns.
Conclusion, the fundamental mathematical operation known as linear transformation uphold the vector addition and scalar multiplication that are important characteristics of linearity because they make it possible to examine space changes while maintaining structure and attributes. They are essential in many branches of mathematics for understanding and working with mathematical objects and systems. Linear transformations are essential with application ranging from computer graphics to quantum mechanics. That's all from us. Thank you.